Welcome to the lesson on the key electricity terminology. Electric vehicles, abbreviated as EVs, rely on electrical systems and components to function. In this lesson, we will discuss some of the fundamental terms that are essential to understanding EVs' electrical aspects. Let us look at our lesson objectives. By the end of this lesson, you will be able to identify the key terms associated with electricity. This will enable you to recognize and decipher the technical terminology related to EVs. Next, you will be able to describe the key terms used in electricity. This will enable you to grasp the meaning and comprehend the basic principles of electrical systems in EVs. There are several terms associated with EV electricity. In this lesson, we will focus on some of the key terms, namely the electric power supply, electric grid, alternating current, abbreviated as AC, direct current, abbreviated as DC, voltage, current, resistance, power, and kilowatt hour, abbreviated as kWh. Understanding these concepts is essential as it provides a foundation to comprehend the inner workings of EVs. We will delve into each of these terms in detail within this lesson. The electric power supply refers to the system that delivers electrical energy to various devices, including charging stations for EVs. The electricity used to charge EVs can be produced from renewable energy sources such as biomass, geothermal, hydroelectric, solar, tidal, wave, and wind, as well as non-renewable sources such as coal, oil, natural gas, and nuclear. To charge EVs, the alternating current from the power supply needs to be converted to direct current. This conversion can happen either outside the EV or within. By utilizing renewable energy sources in the electric power supply, we can further enhance the sustainability of charging EVs. The electric grid is an interconnected network of power lines and other infrastructure that delivers electricity from power plants to homes, businesses, and factories. The electric grid connects power plants, substations, and homes, ensuring the flow of electricity. The electric grid is the interconnected group of power lines and associated equipment for moving electric energy at a high voltage, abbreviated as HV, between points of supply and points at which it is delivered to other electric systems or transformed to a lower voltage for delivery to customers. It is an intricate system designed to provide electricity all the way from its generation to the customers who use it for their daily needs. The connection between the electric grid and EVs primarily occurs during the charging process. EVs are connected to the electric grid through charging equipment, such as charging stations or home charging units. The electric power supply and the electric grid are interconnected but represent different aspects of the electricity distribution system. The electric power supply is a component of the larger electric grid. The electric power supply focuses on generating and delivering electrical energy, while the electric grid encompasses the entire infrastructure that enables the transmission and distribution of electricity. Imagine electricity flowing in a wire like water flowing in a pipe. Alternating current is like water that keeps changing its flow direction. Electrons flow in one direction and then quickly switch to flow in the opposite direction, repeating this pattern continuously. In our homes, AC is the type of electricity that comes from the wall outlets. EVs have one or more electric motors that make the car move. Some electric motors work with AC, but there are also other EVs that use direct current to power their motors. So, just like different cars use different types of fuel, some EVs use AC to run their electric motors, while other EVs use DC. As depicted in this image, you will notice the AC voltage moving back and forth between positive and negative. This alternating nature of AC electricity is what makes it effective at powering various devices. Direct current is electrical current that flows in one direction only and keeps a steady positive voltage without any ups and downs as depicted in this image. DC is particularly useful for various electronic devices and applications that require a steady and stable power supply. The batteries of EVs store power in DC form. The high-voltage power from the battery pack is then fed to the motor controllers, which convert it into the appropriate currents and voltages needed to drive the electric motors. Additionally, in the context of EV charging infrastructure, DC charging is primarily used for fast charging, commonly referred to as Level 3 DC fast charging. Level 1 and Level 2 charging use AC power, which is then converted to DC within the vehicle's onboard charger. Overall, DC plays a critical role in various electrical and electronic applications. Imagine you have a water hose connected to a faucet. The water pressure in the hose represents the potential voltage in an electrical circuit. When you turn on the faucet a little bit, the water flows out of the hose with low pressure. This low pressure can be compared to a low voltage in an electrical circuit. Imagine turning the faucet handle further, increasing the water pressure in the hose. The water now comes out with more force. This increase in water pressure is like increasing the voltage in an electrical circuit. Likewise, when you increase the voltage in a circuit, the electrical energy flows with more force, allowing devices like motors to operate more effectively. So, just as increasing the water pressure in a hose makes the water flow with more force, increasing the voltage in an electrical circuit provides the necessary energy for electrical devices to function properly. Voltage is the driving force that pushes electric charges through a circuit, much like water pressure drives the flow of water through a hose. Voltage is measured in volts using the symbol V. As depicted in the bottom right image, the EV is being charged, and the voltage is 242 volts. Voltage represents work per unit charge, meaning it measures the force that pushes electric charges through a circuit. Voltage could also be abbreviated as E, which stands for electromotive force. Voltage is a critical factor in EVs as it determines the amount of electrical energy available to power the vehicle's components, including the motor and battery. Imagine a busy highway with cars passing you. In this analogy, the cars represent electrons, and the highway symbolizes the electrical circuit. Just like how we measure the rate of traffic flow in terms of the number of cars passing a specific point on the highway, current measures the rate of electron flow in a circuit. The more cars that pass a point on the highway in 1 minute, the higher the traffic flow. Similarly, the more electrons that pass a point in the circuit per second, the higher the current. The rate at which electric charge flows in a circuit is called the current. The unit of measurement is ampere, abbreviated as A. It could also be abbreviated as I for intensity. The more amperes of current, the greater the flow of electricity. Current represents how quickly electricity flows and powers devices. As depicted in this image, the 32 by 32 amps on the vehicle's dashboard indicate that the car is currently charging at 32 amps. The initial 32 refers to the current amperage, and the next 32 refers to the maximum amperage that the car can accept. The higher the amperage, the faster the car will charge. However, the amperage is also limited by the car's onboard charger and the electrical circuit that it is plugged into. Current is essential for EVs as it powers the flow of electric charge from the battery to the motor, enabling the vehicle to move. Resistance can be compared to the width of the pipe. As depicted in the image, a pipe with a large diameter will have low resistance compared to a pipe with a small diameter with a high resistance. When automobiles are driving on an interstate and there is an accident, it causes resistance to the traffic flow. Resistance is the opposition to the flow of current. It is measured in units called ohms, represented by the Greek letter omegoi. It depends on various factors, including material properties, length, cross-sectional area, and temperature. Resistance is a critical factor in EVs as it affects the efficiency of the electrical components, such as motors and batteries, and influences the range and performance of the vehicle. Consider two EVs, Car A and Car B. Car A has a lower power rating compared to Car B. Its electric motor can produce only a limited amount of power, for example, 50 kilowatts, abbreviated as kW. Due to this, when you step on the accelerator, Car A accelerates at a relatively slower rate. Car A might take some time to reach higher speeds, and its maximum achievable speed might be moderate. Car B, on the other hand, has a higher power rating compared to Car A. Its electric motor can produce substantial power, for example, 300 kilowatts. When you press the accelerator, Car B accelerates rapidly and can achieve faster speeds. Car B has a higher maximum speed compared to Car A. The difference in power between Car A and Car B affects the acceleration and maximum speed. Car A with lower power takes more time to accelerate and has a lower maximum speed, while Car B with higher power accelerates quickly and can achieve higher speeds. The rate at which electrical energy is converted to another form is called power. P equals A times V, where P represents power, measured in watts, abbreviated as W. Current is measured in amperes, A, and V represents voltage, measured in volts. The unit of power is the watt. The power of a device is equal to the product of the voltage and the current. This means that the power of a device can be increased by increasing the voltage, the current, or both. Power is crucial in EVs as it determines the rate at which electrical energy is converted and transferred, influencing the vehicle's acceleration, range, and overall performance. In electrical systems, the concept of ground often refers to the reference point or the starting point of the circuit. Ground serves as a common point of reference for voltages. In many circuits, current flows from a source, like a battery, through various components and then returns to the source through the ground connection. Regarding vehicles, they often have common grounds throughout the vehicle. This means that different electrical components in the vehicle are connected to a common ground point. This ensures a consistent reference point for electrical signals and prevents unwanted voltage differences between different components. It helps maintain stable and reliable electrical connections within the vehicle's systems. This image depicts a simple electrical circuit with a power supply, fuse, load, and ground path. The power supply is a 12-volt battery, the fuse is a 10-amp fuse, the load is a light bulb, and the ground path is a wire that connects the light bulb to the battery negative terminal. The electricity flows from the positive terminal of the battery through the fuse into the light bulb. The light bulb converts the electrical energy into light and heat. The current then flows back to the battery negative terminal through the ground path. The fuse is there to protect the circuit from overload. If the current flowing through the circuit exceeds the fuse's rating, the fuse will melt and break the circuit, preventing damage to the other components. The ground path provides a safe path for the current to flow in the event of a short circuit. If a short circuit occurs, the current will flow through the ground path instead of through the light bulb, preventing the light bulb from overheating and burning out. This is a very basic electrical circuit, but it illustrates the basic principles of electricity. More complex circuits may have multiple power supplies, fuses, loads, and ground paths. However, the basic principles remain the same. When you receive your electricity bill, it includes a measurement of your energy consumption in kilowatt hours, kWh. For instance, if your electricity bill shows that you have used 200 kilowatt hours a month, this means that over that period you have consumed 200 units of electrical energy, each equivalent to 1 kilowatt hour. Understanding kilowatt hour helps you gauge and manage your energy usage. It allows you to monitor how much electricity you are consuming. Kilowatt hour is a unit of energy used to measure energy consumption or generation. In relation to EVs, kilowatt hour indicates the battery's capacity, illustrating the amount of energy it can store. A kilowatt, abbreviated as kW, is a unit of power equal to 1,000 watts, W. 1 kilowatt hour is the amount of energy used by a device that consumes 1,000 watts for 1 hour. For example, a 100-watt light bulb uses 100 watts of power per hour. So, if you leave it on for 10 hours, it will have used 1 kilowatt hour of energy. An average home consumes 3,100 kilowatt hour of energy a year. An electric car consumes an average of 2,000 kilowatt hour of energy a year, which translates to 6,000 miles. In summary, a kilowatt hour provides information on the quantity of energy the battery can supply over a given period. Let us recap what we have covered in this lesson on key electricity terminology. Understanding these key terms is essential to comprehend the basic principles of electrical systems and EVs. The electric power supply is derived from various renewable and non-renewable energy sources, including biomass, geothermal, hydroelectric, solar, tidal, wave, wind, coal, oil, natural gas, and nuclear. The electric grid represents the vast interconnected power generation and distribution system, ensuring electricity reaches our homes and charging stations. Alternating current is the current that flows in one direction for a certain amount of time, then reverses direction and flows in the opposite direction for the same amount of time. This cycle repeats itself continuously. Direct current, DC, is the current that flows in the same direction all the time, unlike alternating current, AC, which changes direction periodically. DC is ideal for electronics and applications requiring a steady power supply. Voltage, V, represents the electric potential difference between 2 points in an electrical circuit. It determines the energy flow and the force that drives electric charges. Current is the rate at which electrons flow through a conductor. It is measured in amperes, A, which is the number of electrons that flow past a point in 1 second. Resistance is the opposition encountered by electric current in a circuit, caused by various factors like the material's properties. It is measured in ohms, omega. The higher the resistance, the more difficult it is for the current to flow. Power, P, is the rate at which electrical energy is converted to another form. It is measured in watts, W. Ground is the point in the circuit where all the currents flow back to. It is also the point where all the voltages are measured from. The kilowatt hour, kWh, helps us measure the amount of electrical energy consumed, giving us an idea of how much electricity is used over time. Understanding these concepts is essential for grasping the fundamental principles of electricity, as these concepts will better equip you to comprehend and engage with the electrical aspects of EVs. Thank you.